All right, so there are two things that we've sort of emphasized since the beginning of the semester about vectors. One of them is you're going to have to be comfortable working with vectors to succeed in this class, or in the second semester course, or in some of the other courses that you're going to have to take as part of your degree program. You're not going to get away from vectors. The second thing is that in our class, we're going to tend to deal with vectors in two-dimensional spaces, which of course makes it a little bit easier to deal with. So one of the things that we'd like to do is go ahead and kind of sort of plant the seed now in terms of how do you go from what we're doing in the first semester physics course to what you're going to need to do in, say, a statics class, for those of you who have to take statics, where you're not going to deal in 2 dimensions, you're going to deal in 3 dimensions. And the thing that I want to go ahead and just make sure is as clear as possible is, for many students, the whole reason I've set up this video is that for many students, they feel like what they did in physics class is different from what they're going to do in a statics class. And what I'm trying to emphasize is that in fact it's exactly the same. There's just a little bit of difference between dealing with vectors in 2 dimensions and 3 dimensions that are worth recognizing. And so hopefully, kind of making you guys aware of what those subtle differences are will make it easier to transition as you keep going further in your degree program. So of course we've talked about vectors, and we've said in 3 dimensions I can set up a vector in unit vector notation where vector A is x component times I hat plus y component times j hat plus z component times k hat, and I can calculate the magnitude of vector A by taking the x component squared plus y component squared plus z component squared, take the square root. So again, this is our Pythagorizing, but just Pythagorizing in 3 dimensions. So what we're going to do then to sort of set this up, and we'll walk through sort of some vector algebra first, and then I'll come back and show you sort of in a more concrete example to try and make this as explicit as I can. But what we're going to do to set this up is we're going to say, I know that I can take anything, in this case vector A, and multiply it by the number 1, and I haven't done anything to change my equation. This time I just happen to use the number 1 that's slightly unique in its form. So I'm using the number 1 written as the magnitude of vector A divided by the magnitude of vector A. Well, what I'm going to do is I'm going to go ahead and distribute this magnitude of vector A on the bottom inside the parentheses. And so what I'm left with is I'm left with vector A is equal to the magnitude of the vector times some unit vector, or some new vector, whatever this is. All right, so here I've got vector A is now the magnitude of vector A times this new vector. And so the big question is, well, what is this new vector? And so that's what we want to, so let's go investigate that. So to make our life a little bit simpler notationally, I'm just going to go ahead and name this new vector A prime. And again, all it is the x component of vector A divided by the magnitude of vector A times I hat, plus the y component of A divided by the magnitude of A times j hat, plus the z component of vector A divided by the magnitude of A times k hat. And again, just like with any vector, I can get its magnitude by taking the x component squared plus the y component squared plus the z component squared. So here's where I'm calculating out the magnitude of my vector A prime. Now, again, what you'll notice is, because I've got a magnitude of vector A squared on the bottom of all 3 of these terms, I can factor that out. And what I'm left with is the square root of 1 over the magnitude of A squared times ax squared plus ay squared plus az squared. Well, again, since this is 1 over something squared underneath a square root, I can pull it out, it undoes that square, and so what I'm left with is my magnitude of A prime is 1 over the magnitude of A times the square root of x component squared plus y component squared plus z component squared. Well, this, of course, is the magnitude of vector A. So what this tells me is that the magnitude of A prime is equal to 1. What that means is that new vector, A prime, is actually a unit vector. So I can think about the way that I'm writing vector A. So when I write it in this form, it seems initially really clunky, but there's something particularly useful about it, because basically what it says is there are two parts here. Vector A is a magnitude times a unit vector. And so we can write this way. So vector A is nothing more than whatever its magnitude is times the unit vector that points in the direction of vector A. So we know, hey, what do you need to make a vector? You need a magnitude and a direction. And so this way of thinking about vector A is useful because it's basically giving us those two pieces. Now, in 2 dimensions, and so here I've got a 2-dimensional vector A. It's got an x component and a y component. And what we're almost always able to do in 2 dimensions is define that vector based on some angle. And so if we take our vector A and rewrite it in that form that we've just seen, so magnitude of vector A times the unit vector that points in the same direction as vector A, so A hat. Notice what we get is the magnitude of A times x component over magnitude of A. Well, the x component is this side, the magnitude of A is this side, and since I've got a right triangle, what that means is I have the adjacent side divided by the hypotenuse in my right triangle. That's just another way of saying cosine of the angle here that I've defined as theta. I can play exactly the same game thinking about the y component in my unit vector. So this is the y component of vector A divided by the magnitude of vector A. So again, in terms of my angle theta here, this is the opposite side to the angle theta divided by the hypotenuse. That's just another way of saying sine theta. So you can see that what we're doing is setting up the idea that if I want to think about the vector A in terms of magnitude times a unit vector, well, there's the magnitude of A, and here is the unit vector. Again, I can always check, because I know a unit vector has to have a magnitude of 1. If I take x component squared plus y component squared, that's cosine theta squared plus sine theta squared. Sure enough, that equals 1. So this does have the right length to be a unit vector, and it lies in the direction of vector A. All we tend to do, so the only sort of difference between what we're doing when we usually break up a vector into components versus what we've written up here is just the fact that we've gone ahead and distributed the magnitude. So this is what we tend to do in breaking a vector up in our physics class, because we've got a vector lying in 2 dimensions that we've defined by some angle relative to a coordinate axis. But if I just factor that out, then I've got it in this form, where I've got magnitude times unit vector. So in general, in our 2-dimensional problems, what we're going to do is we're going to say, I'm going to have a plus or a minus because it's going to point in the either plus or in the positive or negative x direction, times a magnitude, times a cosine of an angle if I've defined that angle relative to the x-axis. That's going to be the x component of my vector A. I'm going to have a plus or minus, depending on whether it points in the positive or negative y direction, times the magnitude, times the sine of my angle defined to the x-axis. That's going to be the y component. If I define theta relative to the y-axis rather than the x, then all that's going to do is switch its trig function. So we've talked about how we're going to break vectors in class up into this form. And so the question sort of becomes, well, why is that what we do? And the easiest answer I can give is, well, we do it this way because as a general rule, angles are easy to define in a two-dimensional space. It's easy to draw an angle relative to an axis if I'm only dealing with things that lie within the plane. So if for an example, right, so here I've got a beam, and we'll see examples like this later in class, and so if I've got a beam that's attached to the wall with a hinge, it's also connected by a cable that's going to hold it to some point up here. There's going to be some additional weight that hangs down here. In this problem, what we'll tend to do, or what will often be given in this problem for us in physics, is we'll be given this, what's the length of this cable, and what's the angle that the cable happens to be making with the beam. In this case, another way of saying what's the angle that the cable makes with the horizontal. So if I have a vector, say here vector A, that runs from the point where the cable attaches to the wall to the point where it attaches to the beam, and I want to break that up into its components, well, we would use our angle theta here, and we'll say, well, that's the same angle theta here, and then I recognize that I've got some x component that's going to point in the positive x direction, given by some cosine theta, because it's going to, the x is the adjacent side. I'm going to have a y component that'll use sine theta because it's the opposite side. And so I will break up vector A into a plus magnitude cosine theta I hat minus magnitude sine theta j hat, since the y component's pointing down. It's got to be negative. And again, if you go calculate that out, it works out that that happens to be 4 meters I hat minus 3 meters j. So this is vector A written in unit vector notation. Again, if you wanted to talk about the unit vector that lies in the same direction as vector A, so A hat, well, basically that's just taking out the magnitude. And so we've got the cosine of theta, 36.9 degrees, I hat minus sine 36.9 degrees j hat. Again, you get your calculator to calculate out those angles, or the cosine and sine of that angle, and you happen to get 0.8 I hat minus 0.6 j hat. And again, just to check and make sure, sure enough, 0.8 squared plus 0.6 squared happens to be 1. So this does have a magnitude of 1, so A hat is a unit vector, and it does lie in the same direction as the vector A. Now, we could also be given distances in the problem. So if instead of given this in terms of a magnitude and an angle, what I could be told is, oh, the beam or the cable comes down 3 meters and over 4 meters. And so again, what we could then do is calculate A in terms of those distances. So we don't need to worry about doing the magnitude times angle. We can just say, well, I know in x I'm going to go over positive 4 meters. So I'm going to go 4 meters in the positive x direction. In y, I'm going to come down 3 meters. So I'm going to go 3 meters in the negative y direction. So we can use our distances in exactly the same way that we would use magnitudes and angles to get our components of vector A. If we then wanted to go calculate the unit vector, well, again, I know it's going to be the x component of A divided by the magnitude times I hat plus the y component of A divided by the magnitude j hat, and sure enough, I get exactly the same unit vector. So in physics class, because we're so often dealing with two-dimensional vectors, we can do it either way. It doesn't really matter. We're going to tend to be given problems in terms of magnitudes and angles, but we could be given the components in terms of the distances that you move in two directions. It's effectively interchangeable in two dimensions. The important thing is it's not interchangeable in three dimensions. So with a three-dimensional problem, it's simply much harder to define everything in terms of angles. In fact, you need two angles to define your direction in a three-dimensional space, and that just becomes problematic. It's just a much more difficult problem. So what we're going to tend to do in your three-dimensional problem, you're basically going to say, well, what's easy to measure are the distances. And so I'm going to use those distances to figure out my direction in exactly the same way we did with the second version of our two-dimensional problem. So if you're given some vector A that points from where this cable connects to the wall to where it connects to the end of the beam, so just like in our previous problem, the only difference is now I've got stuff going on in the x direction, the y direction, and the z direction, so I've got three-dimensional stuff. Well, I can still define my angle in terms of how much do I move in the x direction, going from this point to that point, how much do I move in the y direction, going from E to C, how much do I move in the z direction, going from E to Z. So it's easy enough to define A in terms of my distances, and then since I can calculate what the magnitude of vector A is, I can calculate the unit vector. So again, just as a simple example, in this case, if we start at E and go to C, you'll notice that what we're going to do is, well, in the x direction, I need to actually go back 3 feet in the negative x. So I start at E is at a positive 3 feet in x. I'm actually moving in the negative x direction. So the x component for vector A is going to be negative 3 feet. That gets multiplied by I hat. In y, well, let's see, y is along the line of the beam, and so I'm coming 4 feet out and then another 8 feet out. So I'm moving 12 feet in the positive y direction. So that's my y component. And then for my z component, again, I need to go down. Down's going to be in the negative z direction, and I go down a distance of 6 feet. So I can basically read off from the picture what the components are for vector A here. And then it's easy enough once I know the components to calculate the magnitude of vector A, just the square root of x component squared plus y component squared plus z component squared. In this case, plugging in those values, it tells me that the magnitude of vector A, this cable has a length of 13.7 feet to connect from the wall to the end of the beam. And so if I want to know what this unit vector is, it's going to give me the direction of this cable, the direction this cable lies along. Well, I'm just going to take my x component of vector A and divide it by the magnitude to get the x component of my unit vector. In this case, negative 3 feet divided by 13.7 feet is negative 0.218. To get the y component of my unit vector, I take the y component of vector A, again divided by the magnitude, that gives me 0.873. To get the z component of my unit vector, I'm going to take negative 6 divided by 13.7, and I get negative 0.436. I can check the same way I always can if I'm saying this is a unit vector. I can check and make sure it has the right magnitude, and sure enough, if I take negative 0.218 squared plus 0.873 squared plus negative 0.436 squared, take the square root of that, I get 1. So this is the unit vector that becomes very useful in terms of figuring out the direction of vector A. So the important thing to take away from all this, again, we won't do a ton of this in physics, simply because we're going to tend to work in two-dimensional problems, and we're often going to be given information in those two-dimensional problems in terms of angles. But there's nothing that says we can't, in our two-dimensional problem in physics, just use distances if that's the information that we're given. And then certainly when we go to work three-dimensional problems in later classes, particularly in statics, being comfortable with recognizing that, hey, this isn't a cosine and a sine, because now I've got stuff going on in 3 dimensions, but I'm just going to deal with it in terms of a x component over magnitude, y component over magnitude, z component over magnitude, because that's really all cosine and sine are in 2 dimensions.